Welcome to Structural Analysis 2 video series. Unit number 4, Stiffness Method. Lecture outline numerical on sinking of a support in a beam. Problem statement as follows. Analyze the continuous beam shown in below figure by stiffness method. If B support sink by 10 mm, draw bending moment and shear force diagram. Take EI is equal to 4000 km square. Now AB span is loaded with the 20 km per meter UDL. AB is equal to 8 meter in length. BC span having a point load at mid span, and BC is equal to 4 meter in length. Moment of inertia of BC is I and moment of inertia of AB span is 2I. Support at A is fixed support, B and C having a roller support. Now first step in the solution, we have to find out degree of kinematic indeterminacy or degree of freedom. Now at A the support is fixed support, so degree of freedom will be a 0. At B and C there is a 1 degree of freedom, that is theta B and theta C. So total degree of freedom is 2 and named as theta B and theta C. So in second point we have to assign the coordinate direction to the unknown displacement. So let assign the coordinate direction. Now these are nothing but the rotation theta B and theta C. Let assume these are in anticlockwise direction, and for anticlockwise the sign convention is positive. Let call it as a d1 is equal to theta B, and anticlockwise d2 is equal to theta C, and it also we're going to treat as anticlockwise as a positive. Now after this we have to see whether there is any external force acting in the direction of coordinate. Now our coordinates are at 1 and at 2. These are nothing but the theta B and theta C. So in that direction whether any external moment is acting at the location of B and at the location of C, that we have to see. But in the given figure there is no any external moment or couple acting at B and C, therefore that value comes out to be 0. Let's call it as AD1, that means external force acting in the direction of coordinate 1, so no, that's why 0, and in the direction of coordinate 2 there is no any external moment, so is equal to 0. Again I repeat, coordinate means theta B and theta C. These are the two coordinates and their direction we consider or assume as anticlockwise positive. So there is no any external force acting in the given system, so the values are 0, 0. Now in next step let's find out the force in the coordinate direction of a restrained structure. Let's call it as ADL. Now keep each span restrained and find out the due to the restraint whatever the moment generated at the restrained end, that we have to find out. Now consider AB span first. Now in case of AB span, when we restrain it, the fixed end moment get generated at A and B, and there is a sinking of a support. So let assume there is a sinking in a downward direction as a positive. So delta is a sinking. Due to the sinking of the support, the moment will generate and it will rotate in a anticlockwise sense toward the displaced end, or toward the its direction is toward the you have to start from the bottom and move toward the open end. So it is in a anticlockwise direction. So same moment will be generated at the far end in anticlockwise direction. Okay, so how to find out that? For that you have to, we know that 6 EI by L square into delta. So this is the formula. Now let's first find out the moment generated due to the restraint condition at end A. So is equal to nothing but the fixed end moment, and second is a moment due to the displacement or sinking of support. So adding these two as MFAB plus minus 6 EI by L square into delta. So that moment is nothing but the MFAB is WL square by 12 because that is a UDL, and positive. Why positive? Because this rotation is in a anti-clockwise direction, both having the same rotation in anti-clockwise direction at both end. Due to the sinking of a support in a downward direction, the moment will generate in anti-clockwise direction, and same will be at end A. So that's why the sign is taken as a positive. So by putting the value MAB is equal to 20 into 8 square divided by 12 plus 12 into 4,000, that is a value of EI. So here we have to take care of a moment of inertia. Moment of inertia of a span AB is 2I. So 6 into 2 become 12, and EI is nothing but the 4,000 divided by 8 square into 0.010 in meter, that is delta. Now after calculating, we will get the net moment 114.17 kilonewton meter. So this is a net moment due to the fixity at A, and it is mentioned here, that is 114.14. Just adding these two, fixed end moment and moment due to the downward sinking. Now let's consider MBA. We are talking about this span AB. So now consider end B. So again there is a fixed end moment MFBA plus minus 6 EI by L square into delta. So MFBA means WL square by 12 plus 6 EI into 2I divided by L square into delta. Again that sign is positive because the moment is in anti-clockwise direction due to the sinking of a support. So putting the value MBA is equal to minus 20 into 8 square divided by 12 plus 12 into 4,000 divided by 8 square into 0.010. So by solving, we have a net moment of minus 99.17 kilonewton meter. So it is in a clockwise direction, and it is shown here just adding these two, fixed end moment and end moment at end B. So finally we have 99.17 kilonewton meter in a clockwise direction. Okay, so these are the calculations related to this first span AB. Now let's move toward the next span, span BC. So let's consider point B point first. So first one is a moment due to the fixity or fixed end moment. So MBC is equal to MFBC plus minus 6 EI by L square into delta. This is a moment due to the sinking of a support. So moment due to the delta. Now this delta we again delta is in downward direction as a positive. So start from the bottom side and move toward the open end. So this moment will be in a clockwise direction, opposite to the previous one, or opposite to this BA. There will be moment in a clockwise direction. Okay, and same moment will be at the far end. You see, this is also in a clockwise direction. Okay, due to the sinking of the support in a downward direction. Now, so that means its sign is minus. For the clockwise, our sign convention is minus. So for point load, now this fixed end moment formula is WL by 8 for point load at midspan minus 6 EI by L square into delta. Now put the value. W is 60 into span is 4 divided by 8 minus 6 into 4,000 divided by 4 square into 0.010 in meter delta. After solving, MBC is equal to 15 kilonewton meter. Now this is a positive, so net moment due to the fixed end moment and moment due to the delta is 15 kilonewton meter. So this indicate net moment of our addition of these two. Now find out moment at end C. So MCB, let's call it as, is equal to minus MFBC. This is a end moment due to the fixity plus minus 6 EI by L square into delta. This is the moment due to the sinking of the support. So due to the sinking of the support, we know that there is a moment generated at C and it is in a clockwise direction. That's why here is a minus sign. So fixed end moment at C is in a clockwise direction, so it is minus. So formula we know that it is symmetrical, so formula remains same, WL by 8 minus 6 by L square into delta. So putting the value minus 60 into 4 square divided by 8 minus 6 into 4000 divided by 4 square into 0.010 in meter. So finally we have MCB at end C minus 45 kilonewton meter. So that value is shown here, 45 kilonewton meter in a clockwise direction. Okay, so this is all about your moment due to the restraint. Okay, now our interest in the calculation of forces in the direction of a coordinate. So we know that our coordinates are at as a theta b and as a theta c at one. Let's call first one is a theta b and second one is a theta c. Now the forces which are acting in the direction of this coordinate, that we have to sum up as a ADL1 and ADL2. So we already calculated now these. This first value is 106.67 at B due to the fixed end moment, and second moment due to the moment due to the sinking is 7.5 kilonewton meter. Okay, so when we add these together, we have 99.17 kilonewton, and it is in a clockwise direction. Now same way at B, due to the fixity, the MFBC is 30 kilonewton, and due to the delta at B the value is 15 kilonewton meter. So by adding we have this final value 15 kilonewton meter in a anti-clockwise direction. So these are the total net moment. These two indicate the net moment which are acting at B, that means in the direction of theta B. So let's take that summation. So first is in a clockwise direction minus 99.17 plus 15. So these two are acting in the direction of coordinate or theta B due to the restrained structure. And second, our second coordinate is theta C, or unknown is theta C. So in that direction, when we keep a structure restrained, these two are acting and their summation come out to 45 in clockwise direction. That's why minus 45. Okay, so these are the two forces. These are the addition of forces when we keep a structure restrained in the direction of a coordinate theta B and theta C. So finally we have minus 84.17 and minus 45. Now let move toward the next step. Determine the stiffness matrix formed by forces in the restrained structure subjected to unit value of d1 and d2, that means theta b and theta c, corresponding to the unknown displacement. So first one, let's consider restrained structure and apply the unit value in the direction of theta b, and that direction is, let's consider, anti-clockwise positive. So by doing so, we will get first column of a matrix. So this matrix is a 2 by 2. So our unknowns are 2. So we have a matrix of a 2 by 2. So let's first find out the coordinate of a matrix. Now let apply the theta b is equal to 1. So theta b, let apply the theta b is equal to 1 due to the application of a rigid joint rotation. Theta b is equal to 1. Same rotation will be happen for the BA side. Theta b is equal to 1. This is a rigid joint rotation. So it is always same for the connecting member. Now keep the far end fixed. So by doing so, we will now this is a first location of a first coordinate, and this is a location of a second coordinate, and we are applying the force in the direction of a first coordinate. First coordinate is theta b. So that is first coordinate. Force is applying in the direction of a first coordinate. So one is indicate it is a first coordinate. Force is applying in the direction of a first coordinate is equal to 1 or unity. So we will get S11 and S21, that means first column of a matrix. So let write down here S11 is equal to S11 BA for the span BA first span plus S11 BC. So is equal to, now here the value will be 4 EI by L. Now moment of inertia of a BA is 2I. Moment of inertia of a span AB is, or BA is 2I. So put here, so BA plus 4 EI by L for BC, because at the B two members are connecting. So we have to consider two moments generated for the connecting member. So by putting the value of L, we have 4 EI, 4E, now I is 2I, putting that, divided by 8 for BA span plus 4 EI by 4 for BC span. So we will get 2 EI. Now find out S21. Now at the far end, S21. So S21 is half moment will be carry at the far end. So that's why instead of 4 you have to take 2. 2 EI by L. 2 EI divided by L is 4. So we have 0.5 EI. Okay. So we having the first column. Now apply the unit rotation for the along the in the direction of a second coordinate. So our second coordinate is theta c, let's call d2, and unit apply the unit rotation in the direction of theta 2 in anti-clockwise direction. So this is a location of our, this is a second coordinate location, this is first coordinate location, and we are applying the unit force in the direction of second coordinate. So the second number indicate the direction of, or the where you are applying the unit force. Okay, so you will get second column of a matrix now. So here at C, let apply the unit force in the direction of a in the direction anti-clockwise direction. Okay, so by applying the force in the anti-clockwise direction, the moment generated is S22. CB indicates span, CB span for along the span CB, and at the far end the moment generated is S12 BC. So again the span is mentioned there. So half will carry at the far end. So this moment, let's calculate the moment. Let's call it as a S22 first is 4 EI by L. So is equal to 4 EI by 4 into CB span, it become EI, and for far end 2 EI by L is equal to 2 EI by 4 and is equal to 0.5 EI. So we having a second column of a matrix. Okay, so let stop here. In a next video we will continue the remaining part. Okay, thank you.